fun with probability distributions. All right, so a probability distribution is a distribution of probabilities. That is all. Moving on. No, it's really that. So X represents the number of possible outcomes in an experiment, and P of X represents the probabilities that go along with those outcomes. And so what we do is we make a list of all those X values and all those probabilities. And when we have an entire list, that list is called the probability distribution because it gives us a sense of the structure of the situation. All right? Very calculator dependent, unless you, I mean, it is possible that you look at these formulas and say, yeah, oh, those look great. I want to use those often. So we will use a calculator. We're looking for a probability distribution for one roll of a fair die. So the outcomes would be 1, 2, 3, 4, 5, and 6. And again, the fair die would be a 6-sided number cube. You know what I'll take as a typo is words to the effect of every time I ask a question about dice, put a little picture of dice. Okay, so just so I remember, you know, most people know what they are, but every now and then. And besides, it'll make my notes look nicer. All right. And there it is. So P of X, in each case, we have a 1 in 6 chance of getting what we're looking for. I got a 1 in 6 chance that I'll get a 1. I got a 1 in 6 chance that I'll get a 2, a 3, a 4, a 5, and a 6. I make a little note at the bottom, as always, P of X should be between 0 and 1. Now, that may seem unfamiliar, like P of X, what the hell does that mean? That's the probability of the X values happening. And so all I'm saying there is that those probabilities that make up your chart, each one of them need to be between 0 and 1. They still have to follow the rules of probability. Now, if I were to add up that P of X column, I would get 6 out of 6, which is equal to 1. So then my question, what should, again, this means sum. What should the sum of P of X be? Well, it should be equal to 1. And the reason why is it accounts for 100% of the outcomes. Because remember, we work in decimal form for probabilities, but they do have equivalent percentages. We say 0.5, the rest of the world says 50%. So when I say 1, the rest of the world says 100%. Right? Right? So we could find the mean and the standard deviation. Using these lovely formulas, or we could do it using the graphing calculator, but you already know. It's happened for most people. In the beginning of the course, it was like, enough of this calculator, I hate it. But the transition for most people has happened, where it's like, whoa, there's a lot of stuff we don't have to do by hand as long as I know how to use this calculator. I really better get on board with this calculator. It's that important. And I show the formulas for that reason. This is, you have me. It's me. I'm your teacher. And because I'm your teacher, you don't have to work with these formulas. There are, and you'll see, I hope, well, I was going to say you'll see. Well, no, only if you don't listen to me, you'll see. But there are teachers that tell you, what the hell? What are you doing with a calculator? Scientific, that's where it's at. I don't know, graphic calculator, get rid of that thing. You got to do all this stuff by hand. And even if they do allow the graphic calculator, They say, yeah, that's cool. I need you to show me all the work. I'm not asking you for that. So if you haven't bought in yet, I don't know what you've been doing this whole time. You've all bought it. All right, so this is a list of data. Fun fact of the day. Lists of data, stat, edit, go into our list menu. I'm going to clear out what I have here. I'm going to hit clear on each of the column headings. Haven't used this editor in a while. This looks like a little Unit 1 action there. And I'm just going to pop in these numbers. It's annoying, but you do have to type in 1/6 6 times. There's another way to do it, but it's not really a shortcut. All right, for those, I will show you though, for those of you who are calculator savvy, there are some. I do want to show you what the shortcut would look like. So if you don't have any interest in this, just please ignore me. Instead of typing 1/6 in 6 times, you can see in this case it wasn't that bad, but if you had to do it like 30 times, that would be pretty annoying. What you can do is in the column heading, for whatever column you want, I'll just do it in L3 for lack of a better place. I hit enter. It allows me to define L3 any way I want. I would create an equation here. What I would do is I would take L1 and multiply it by 0. And then add to that 1 divided by 6. Because what happens is, if I just type in 1/6 as the column heading, the calculator doesn't understand that. Right? If I type in 1/6 in the first cell, it's just going to apply whatever I do for the first cell. But if I do this operation, what it does is it allows for me to put as many entries in L3 as I have in L1. By multiplying it by 0, it's getting rid of all of these numbers and adding 1/6 to 0 in each case. And so it's going to populate it for a corresponding number of values, 1/6. All right, so you see it does it all in one shot. Now, again, 6 values, it's not really necessary. 30, 40, 50 values that are all the same, definitely necessary. All right, but on a test, I'm not going to ask you to put in 50, 60 values. So, it's really just fun fact stuff. All right. So anyway, we want to find the mean and standard deviation. You'll notice how we have the different notation here from the first unit. This is a population mean. And this is the population standard deviation. All right. Samples are for subsets, meaning part of something. Right. So you have a classroom. A subset of the classroom might be like only the people wearing hats. All right. So it's part of the group. If I define a population, I'm saying 100% of whatever it is I'm talking about. All right, so if I'm talking about the population of humans, I would need every single human, 100% of the humans. If I'm talking about the population of light bulbs in this building, I would need every single light bulb. This is a population because of this fact. The probabilities add up to 1, which means that they're accounting to 100% of the outcomes, which define every probability distribution as a population. All right. So, why do we need to know that? Well, if I hit stat, calc, one bar stats. We're going to find the mean and standard deviation exactly the same way we did in Unit 1. Stat Calc 1. I have information in L1 and L2. If I didn't have anything in L2, I would just hit second 2 to put an L2 in there. All right, second 1, second 2 to give me a list 1 and list 2. Then I hit calculate, and it gives me this information. The reason why I needed to know the difference between population and sample means is because of this. Let's pop it in over here. We were working off of S in the first unit. Well, it was mine, now it's ours. But now I don't have any information there. If I didn't know to be on the lookout for sigma, then I would think, okay, my calculator's broken, I did something wrong, something terrible's happening, I'm going to fail. Right? But I now know, because it's a population standard deviation, I wasn't looking for that to begin with. What I need is this one. So this one is not needed. And, well, the good news is the calculator knows that. It knows that because you're dealing with 100% of something that you could not possibly be asking about a sample, so it doesn't report it. It does not distinguish between the Greek symbol mu, which stands for population mean, and the X bar. These two mean the same thing as far as the calculator is concerned. All right, you just have to know the context. So the mu is 3.5, and the sigma is about 1.707, 1.708. But it's all about reading the display. The calculator, or the Texas Instruments anyway, they made an executive decision a long time ago. They wanted to make sure that their functions were as concise as they could be, almost to a fault. And so they merged a lot of things that maybe shouldn't have been merged. There should be a submenu in your calculator that asks population or sample so that it can give you a complete display for each situation. They just decided not to do that. And so we just have to live with the results. So they have it all in one place. We just have to parse out what's what. All right? So that's how you find mean standard deviation. Now what we have here is a display or a probability distribution where all the probabilities are equal to one another. That's known as a uniform distribution. All right, that's a uniform distribution. And the reason why is when I graph these outcomes in the form of a histogram, I'd have 1, 2, 3, 4, 5, and 6 as my set of outcomes. Each one would occur 1/6 at a time. My frequency of relative frequency histogram is what it's called. So anything involving a probability, we call a graph of a probability distribution. All right? But anyway, the heights of this distribution are all the same. All right? It's unchanged from outcome to outcome. So that's why they call it uniform. But there could be some fluctuation. If there's fluctuation, then it's not uniform. And if it's not uniform, it could be other types of graphs. But it's the same types that we had in the first unit. It could be a normal distribution. It could be something that's bimodal, like maybe it has two peaks, and a valley in the middle. You could have something that's skewed in one direction or the other. There are a lot of different possibilities. Right? So that's really what we're going to focus on to some extent, anyway. This is page 35.